How you doing, everybody? This is going to be the electronic version, the recorded version of our Thursday normally scheduled 1 to 3 class doing motor installations as per Section 28 from your Canadian Electrical Code books. Uh, we are going to go through and complete this motor calculation as you see. So I will give you an observation and tell you when is a good time for you to pause your video so that you can record the information and follow along with me for the calculations to determine the conductor's ampacity, the overcurrent ampacity, the disconnect sizing, your overload calculation, your junction box sizing, and realistically everything that's included with hooking up this one specific motor. So this one specific motor has some specifications to it. It's going to be fed with TW75 conductors that are constructed of copper, and we have 75 degrees Celsius termination temperatures. So we are going to go through and we are going to look at terminating this motor, sizing disconnects, overcurrent devices, using the rating or setting the overload component, and looking at the installation of these conductors to suffice this 15 horsepower 208 volt 3-phase service factor 1.2 continuous duty service class A motor. Okay, so right now would be a good time for you to pause this video so that you can observe all the things that I'm going to start talking about when we go through and start looking at this calculation based on the values that we see in section 28, as well as the tables that section 28 refers you to. So right now will be a good idea just for you to take a second, pause this video, record all this information about this motor, and we'll continue in just a second. So we are looking at a 15 horsepower, 208 volt, 3-phase motor with a service factor of 1.2, continuous duty class A motor. Okay. Typically, these are going to be squirrel cage motors or auto starting motors, things like that. These are going to be just standard 3-phase motors when we're looking for overcurrent protection, sizing our conductors, utilizing section 28 to, our capabilities so far. At this point in time, my very first step is to go through and calculate what my full load current rating is going to be. I know that I have a 15 horsepower motor and it's connected to a 208 volt source and it's a 3-phase motor. So I can go right to table 44 and I can find throughout table 44 under the 208 volt column, scrolling down on the far left hand side, 15 horsepower, to figure out that this motor is good for 46.2 amps FLA, full load current. 46.2 amps. And I came up to that value from table 44 for a 3-phase AC motor. And that was based on the 15 horsepower, 208 volt, 3-phase thing that I went to table 44. The first direction that I would like to go is sizing my conductors and looking at what size of conductors I'm going to need to supply to this motor to deliver 46.2 amps as a full load current rating coming from my table 44. Those rules are coming from section 28, 104, and 28, 106. 28104 talking about termination temperatures and installation ratings of conductors. 28106 talking about the motor itself and the continuous duty service of that motor. Since it's a continuous duty service motor, I'm going to be observing my full load current rating multiplied by what I see in section 28106 of being 125% my full load current rating for my conductors. That would therefore translate to 46.2 times 1.25 to achieve that multiplier, or to achieve the minimum ampacity of my conductors for this specific application. So I'm 46.2 as an FLA, and I'm 125% the FLA to size the minimum ampacity of my conductor. If I go through and I do that calculation, I should end up somewhere in the 57.75 amp range, somewhere around there, 57.75 as my calculated minimum ampacity for my conductors. Now, this is a three-phase motor, so I have a red, a black, and a blue feeding this motor, as well as I'm going to tie in a bonding conductor. I'm going to throw a bonding conductor in there anyways, just to be safe. So at this point in time, I'm 57.75 amps as a minimum capability of my conductor. I would therefore take my 57.75 amps and I would go right to table 2 to figure out which conductor I'm going to supply to suffice this 46.2 amp full load current rating of the motor based on a continuous duty service factor. 57.75 amps, take that to table 2. Once you take that number to table 2, you should come up with the fact that you're going to install a number 6 conductor with TW75 insulation rating on it. And it's always a good idea to record its available ampacity in brackets after you have selected a conductor. This saves us a step when we're talking about voltage drop calculations. So we are looking at this conductor being 57.75 amps as a minimum, but they don't make a 57.75 amp conductor. So I take that value and I go to table 2 and I select a number 6 TW75 conductor because I know that my conductor's ampacity or the insulation rating of my conductor is 75 degrees Celsius, and I have a 75 degrees Celsius termination temperature on all of my components. And that suffices the Class A thing. But we'll talk about the expansion of the rule in just a minute when we start looking at that Class A thing. So in this case, number 6, TW75, I need a red, a black, and a blue. This is a 3-phase motor. And I'm also going to incorporate a bond into this. That's sizing my conductors to feed this motor. Check mark. We're good to go. I will record that up here. Number 6, good for 65 amps. TW75 insulation on those conductors. The next portion that I would like to run through is your overload protection over here. Now, either with myself or Mr. Pratt, you've been connecting overload protection for all the motors that you've connected so far in installation methods. And that overload protection is set or rated at the service factor of that motor. So in this case, when we're looking at the service factor of the motor, I'm operating at a 1.2 service factor for this motor. This means that it's a very trustworthy motor. I can trust this motor. If I have a service factor of 1.2, my multiplier comes from 28,306. Section 28, Rule 306. And that says that if it's going to be a service factor of 1.15 or less than 1.15, or it's not marked, then your multiplier is 1.15. But if it's 1.15 and greater, then it has a multiplier of 1.25. So in this circumstance, my service factor is marked at 1.2, which would be 1.15 or greater. So I almost have exactly the same calculation. Again, I take my FLA and I multiply that by 1.25. And that's because of my service factor. And it's marked, it's stamped on the nameplate that it's 1.2. If that nameplate had no marking for that service factor, or in the equation or in the question that I might give you, that your service factor was not marked, then you cannot use the 1.25 multiplier that you see here in this specific equation. It doesn't exist. There is no marked service factor, or the service factor is less than 1.15. In that case, it's a very untrustworthy motor. And I'll show you those means in a minute. 46.2 amps multiplied by 1.25 as a multiplier, because your service factor is 1.2. Your 1.25 is your multiplier. In that case, you come up to relatively exactly the same number, being 57.75 amps. And this is going to be the rating or the setting of your overload component down here. So now your overloads are going to be set to 57.75 amps. Just like on the IEC starter, you'll see that there's a dial to set your overload component to. The next time that you're in Installation Methods lab, take a look at the IEC starter that you're wiring to perform the task of that motor's operation, and you will see a little blue dial. And you can set that overload to its capable component of 57.75 amps. Now, that 57.75 amps is very interesting for us because it's also the rating or the minimum setting of our conductors to size for this 46.2 amp full load current rating, 15 horse, 208 volt, 3-phase motor with a service factor of 1.2, continuous duty, and a Class A installation. It also comes down to being the same calculation. So when you move forward, you should be observing that service factor at the same time as doing your conductor calculation. It's the same multiplier, 125%, or a multiplier of 1.25. And you come up to the same number every single time based on the service factor being 1.2. So it is two different code rules. However, it's the same multiplier. It's two different code rules. There's two different sections within section 28. It's two different rules, but it's the same multiplier. So be very careful of this in the future. This might save you a little bit of time. We've already calculated that 57.75 amps would be my conductor's minimum ampacity. I took my 57.75 amps and I went right to table 2. I found that my number 6 at 75 degrees Celsius was good for 65 amps. That was my chosen value. This proves to you that your overloads protect your conductors. Now, I understand that there was something going on with your motor installation book, your motor control book, and we'll address that on Friday. That's not a big deal. But your overloads are protecting your conductors. Your overloads will open at 57.75 amps. And they'll allow a little more current for inrush to get that motor up to speed, but only for a short period of time. And keep in mind, you're going from the Canadian Electrical Code Book here. I'm showing you the code rules to suffice this 15 horsepower, 208 volt, 3-phase motor. So your overloads are protecting your conductors. Your conductors are rated or set for 65 amps. And your overloads are set to trip at 57.75 amps. But in normal operation, you still have to look at this number, the 46.2 amps. In normal operation, that 15 horsepower motor at 208 volts should realistically never draw more than 46.2 amps. So your overloads are there as a backup, just in case your motor fails. But then your overloads are also observing the capabilities of your conductor. And what motor control won't show you is your overcurrent capabilities. And it varies between textbooks. You have to understand that motor control books are based on not the code, different theories of electricity. Okay, so for this example, we have 3 different capabilities of overcurrent protection, but the one thing that's protecting my conductors is my overloads. And those overload contacts are exactly the same ones that you wire in to your motor control circuits every single week in installation methods with either myself or Mr. Pratt. Absolutely. 95 and 96. Bottom left-hand corner on your overload relay for your IEC starter. You wire in those overloads to protect that motor that you fire every single week, whether it's with a flow switch or a start-stop station or a parallel start-stop station. It's the same motor every single time, 3-phase. And it is 208 volts. However, it's not 15 horsepower. It's a lot less than that. So anyways, we have a few different options when we start into consideration for our overcurrent protection. And here is where you will figure out that your overcurrent protection does not protect your conductors. It does not. And I'll show you exactly how it doesn't in just a minute. When we go through and we look at overcurrent protection, we're concerned with 28200. 28200. 28200 tells us that we realistically have 3 different types of most commonly used overcurrent protections. And those are time delay fuses, TD representing time delay fuses. We also have non-time delay fuses. And we also utilize circuit breakers. Now, I know that excerpt from Motor Control talks about, a 10 amp motor and we install a 20 amp overcurrent device. That's not the same case for us with the Canadian Electrical Code Book. I have different values for different types of overcurrent protection. And coming from 28200, it also sends you to table 29. Looking at time delay fuses, non-time delay fuses, and inverse time circuit breakers, or we just call those normal circuit breakers. Your multipliers are generated from table 29 in your Canadian Electrical Code Book. And for a time delay fuse, you're looking at 175%. Your full load current ampacity of your motor. For a non-time delay fuse, you're looking at 300%. Your full load current ampacity of your motor. Or for a circuit breaker, you're looking at 250%. Your full load current rating of that specific motor generated from, once again, table 44. That's exactly where we came up with the FLA for this 15 horsepower, 208 volt 3-phase motor. So I can observe my 175% of my full load current rating to properly size a time delay fuse. So I would take 175% times 46.2 amps and come up to a maximum value. Do the same thing with a non-time delay fuse at 300% times 46.2 amps and come up to a maximum installed value. Same thing with a circuit breaker, 250%, the full load current rating of that motor times 46.2 amps to come up to maximum values. Maximum installed values. This is a good time for you to hit pause, just to go back and observe the rules from 28200 and have a look at table 29 when we're looking at overcurrent selection of devices. Now, also, when you read through 28200, you will see, and it's very specific in the code book, that you cannot exceed these calculated values. Very specific in the code book. Once you go through and you do all these calculations for your 3 individual overcurrent devices, once you find those numbers, they cannot be exceeded. So go through 28200, observe table 29, look at your opportunities for overcurrent devices. Now will be a good time for you to hit pause on this video, go through and do those calculations with me. We'll do this together. I'll put the calculations on the board in just a second. But now will be a good time for you to pause this video so that you can come back and observe what's going on with this motor calculation. Okay, so now we're looking at time delay fuses being 175% my full load current rating of my motor. I'm looking at non-time delay fuses being 300% the full load current rating of my motor, and circuit breakers being 250% the full load current rating on my motor. I'm going to size all 3 here, just so we have a conversation topic to move forward into motor control and motor operation, and sizing your conductors and circuits for motors based on your section 28 of your Canadian Electrical Code book. So I'm looking at my first one being a time delay fuse, and I'm 175% my full load current rating for a time delay fuse. That's coming directly from the rules from 28200 going into table 29. So I am 1.75, 175% times 42.6 amps as my FLA to calculate that my maximum installed fuse size for a time delay fuse would therefore be 74.55 amps. A non-time delay fuse is rated at 300% the full load current rating of the motor, which is 46.2 amps. So 46.2 times 3, or 300%, that leaves me up to 138.6 amps as a maximum calculated overcurrent device. A circuit breaker, 250% my full load current rating being 46.2. 46.2 times 2.5 gives me 115.5 amps. Maximum calculated values. Maximum. I cannot exceed these values, and that is specifically stated for you in 28200 when they refer you to section 29, or sorry, table 29. I cannot exceed these values. These are maximum calculated values. So if you have chosen a time delay fuse, you do this calculation and you call the wholesaler and you say, hey, what's up, guys? I need a 74.55 amp fuse. Can you put 3 of those on the counter? And I'll be there in about 20 minutes to come and pick those up. Only the 74.55 amp fuses, though. They're going to say, no problem. You come in whenever you get a chance. You just swing on by. No big deal. 74.55. Ah, man, I got too many of those. Thank you for coming in for those fuses. They're going to say, see you soon. Hang up the phone. Wonderful. You show up to the wholesaler, and everybody's having a laugh while they're having a coffee because they don't make a 74.55 amp fuse. They don't make a 138.6 amp fuse for a non-time delay option. And you sure as hell can't go to the wholesaler and buy a 115.5 amp fuse, circuit breaker, 115.5 amp circuit breaker to install for the specific motor. So what do? Well, we do have a table in our code book that tells us the nominally installed sizes of fuses, and that's coming from table 13. Table 13 will give us nominally installed sizes of fuses. However, I cannot exceed these values that are shown or calculated based on my rules from table 29, coming directly from 28200. So I can take these calculated values and I can go to table 13 to figure out the nominal sizes that the CEC recognizes for overcurrent protection. And in that case, if I'm looking at a time delay fuse, I know that I can't exceed 74.55 amps. So I go to table 13 and I should be allowed to install a 70 amp fuse. Oh, 175. Wait a minute. 1.75 times 46.2. 80.85. Oh my goodness, I made a mistake right there. Oh no. And that's totally on a recording. Oh my goodness. 46.2 times 1.75. Oh no. 80.85. Oh, I made a mistake. Look at that. Nobody's perfect. 80.85. How did I come up with the other value? 42.6 times 1.75. Yeah, there it is. All right, sorry, I had my numbers backwards. I'm sorry. My sincerest of apologies. I made a mistake on the very first one. My goodness. You'll never forgive me. I know it. I'm actually looking at 80.85 amps as my maximum capability for that time delay fuse. My goodness, my sincerest of apologies. I'm not going to re-record that. So yeah, I made a mistake. That's my first one for the year. 80.85. I better double check all my other numbers here. Okay, so I'm 3 times 46.2, 138.6. Yeah, that one checks out. 46.2 times 2.5, 115.5. Those all check out. Okay, my sincerest of apologies. So I'm looking at that time delay fuse being 175%. I switched those two numbers. I was 42.6. That was the wrong thing to do. It's actually 46.2. My mistake. 80.85 amps being my maximum calculated value for the installed fuse size for this time delay fuse. I go to table 13 for my time delay fuse having a maximum value of 80.85. I should be able to get away with an 80 amp fuse installed for a time delay. For a non-time delay fuse, I'm looking at 138.6. So to size a non-time delay fuse, I'll grab my code book right here. We'll do this all together. Go to my table 13 right here for a non-time delay fuse. Okay, set at no more and no greater than 138.6. I go through and I look at my table 13 right here, and I see that my next available size, I'm 110 down this way. I see a 125, but then I'm 150. So I'm going to have to drop down to the 125 thing. So for a non-time delay installed fuse, an NTD, I am 125 amps for a non-time delay fuse. And then once again for the circuit breaker at 250%, my FLA, I calculate 115.5 amps. So for a circuit breaker, I cannot exceed that 115.5. In that case, I go back right to my table 13 right here, and I see I cannot put in the 125 because that far exceeds my 115.5 amp calculated maximum. I have to install a 110. 110 amp circuit breaker. Once again, I sincerely apologize for this 175 thing. That was my mistake. Okay, that's my one mistake for the year. I sincerely apologize about that. Okay, 80.85 for a time delay fuse. Okay, 138.6 for a non-time delay, 115.5 for a circuit breaker. My installed values would therefore be an 80 amp time delay, a 125 amp non-time delay, and a 110 amp circuit breaker. That would be my overcurrent protection. Now would be a good time to hit pause and make sure that you have the same values recorded as myself. Okay, when we're looking at our installed values versus our calculated values. Now would be a good time to hit pause, and everything is based on the full load current rating of the motor. Okay, so based on the full load current rating of the motor, I size my overcurrent protection, whether it's a time delay, a non-time delay, or a circuit breaker. All right, and I came up to my calculated values being 80.85, 138.6 amps for a non-time delay, 115.5 for a circuit breaker. My installed values are 80 for a time delay, 125 for a non-time delay, and 110 for a circuit breaker. Good things to know. Okay. Here's how you determine this in the field. All right. It depends upon which style of overcurrent device that you're going to install. And I want you to observe this just for a second because we're going to talk about real installations, real things that happen in real life. What ends up happening with your installed overcurrent devices being an 80 amp, a 125, or a 110 for a 46.2 amp motor. 80 amps for a 46.2 amp motor, 125 for a 46.2 amp motor. Come on, man, give me a break. Really? That's 300% the full load current rating of that motor. You have to understand that motor should never ever draw more than 46.2 amps. But we have to accommodate for that. So herein lies the problem. Here's the issue. And here's how you have to start thinking towards the future. These are your installed values down here. I'm getting rid of your calculated values because you should have that recorded already. Here's what happens when you try to install an 80 amp fuse or a 125 amp non-time delay fuse or a 110 amp circuit breaker. The circuit breaker, not such a big thing. All right, this motor, 46.2 amps, better never draw more than 46.2 amps. So if I took my time delay fuse operation, that would mean that I'm installing 80 amp fuses into a disconnect as a time delay operation. At that point in time, I know that I'm installing 80 amp fuses for the overcurrent protection of this motor. That means that they're going to go into a minimum 100 amp disconnect. Okay. If I chose non-time delay fuses, they're 125 amps, which means I can actually install a 125 amp fuse into a 125 amp disconnect. Okay. If I chose a circuit breaker, this disconnect might turn into something more like a spa pack. Okay, a spa pack meaning, like an exterior panel and how you hook up like a hot tub or a very small panel that you can put remotely somewhere else in a factory, for your installation of set of 15 horsepower 208 three-phase motor. And at that point in time, a 110 amp overcurrent device, that's fine. And that's going to go into your panel. That's no big deal. But these two values are interesting to us. Okay, 80 amp fuses going into a 100 amp disconnect. That's fine. I would size that disconnect to being 100 amps to accommodate an 80 amp fuse. That's no problem. We can get away with that. And then if I chose a non-time delay overcurrent device like this one here, you're telling me 125 amps for a non-time delay fuse in a 125 amp disconnect? Yeah, okay. Those check out. That checks out. That's going to go into your panel or a molded case switch, like a spot pack, something like that. Very similar to what you would use for a hot tub, like I said. No big deal. That's fine. But you're actually going to sit there and tell me that you're going to put in a 100 amp disconnect with 80 amp fuses inside this disconnect, 1, 2, 3 of them inside that disconnect, with number 6 conductors that are only good for 65 amps to protect a motor that realistically should never draw more than 46.2 on a 125 amp fuse? That's 300% is full load current rating. You're going to sit there and you're going to do that installation where you put in a 125 amp disconnect with 125 amp non-time delay fuses, and you're going to connect number 6 to that? Yeah, that's the calculation. Absolutely. That's exactly what we're alluding to this entire time. Your number 6 conductors are good for 65 amps. Their calculated value should never exceed 57.75, and that motor should never draw more than 46.2 amps. So yeah, why not? Why not? Let's put in the 80 amp fuse in the 100 amp disconnect and call this a time delay installation. And we'll get rid of the non-time delay thing. We'll get rid of the circuit breaker thing, because this is probably more of the common value that you would do for an installation for a motor like this. 80 amp fuses inside of a 100 amp disconnect, that's a big check mark right there. You've done that calculation correctly. And we can eliminate these down here. We don't have to necessarily worry about our different types of overcurrent devices. We know our conductors that are being installed. So at this point in time, our overcurrent device is calculated for a time delay value at 80 amps installed. Or what we actually calculated for that overcurrent capacity to be was 80.85 complete amps calculated. So right now for this situation, you are going to install number 6 conductors, a red, a black, and a blue, going to feed a motor that is rated for 46.2 amps as a full load current rating with a service factor of 1.2, rating or setting your overloads at 57.75 amps from load side of the disconnect through your overcurrent device into your overload into this junction box and feeding your motor, which should never draw more than 46.2 amps, coming from table 44. Your installations are based on this class A, and we know that we're running TW75 conductors, and everything is terminated at 75 degrees Celsius. So if you've done this calculation correctly, you will see that yes, you are going to terminate number 6 TW75 conductors into a 100 amp disconnect with 80 amp time delay fuses. You're going to set your overloads to 57.75 amps, and now you possibly might see that your overloads are actually protecting your conductors. Because that 80 amp overcurrent device isn't doing anything for your conductors. Your conductors are only set and rated for at no more than 65 amps. So you have to be very careful when you're going through and you're looking at these different code rules, because we're talking about Canadian Electrical Code section 28 here. We're not talking about industrial motor control. Industrial motor control, I read that excerpt. It also says that you have a 10 amp motor with a 20 amp overcurrent device. Give me one example for what we know right now that would have a 10 amp motor with a 20 amp overcurrent breaker. breakers are set at 250% the FLA. That'd be a 25 amp breaker. Like that doesn't make sense. So be very careful with that rule. We'll expand on that a little later on. But now you have to look at this overcurrent device protecting the motor itself. 80 amp overcurrent device installed in a 100 amp disconnect using number 6 conductors that are only good for 65 amps. So here's how this kind of situation runs. And here's the explanation on why your overloads are looking after your conductors and why your overcurrent is looking after your motor. Here's the explanation. By this time in electronics, I hope that you've scoped something. You used an oscilloscope for something. When you use an oscilloscope, majority of the time you're observing a voltage or voltage characteristics. You can use a channel on an oscilloscope to scope current at the same time as well. So if everything is going smoothly with this motor, and this motor is working at full capabilities and full capacity, you can scope your current to be an RMS value right here of 46.2 amps, like that. A root mean square value, an RMS value of current, looking at an AC sine wave very similar to this. That means everything is going appropriately. That's fine. Then, all of a sudden, you add a little bit more load to this motor. You kind of make, or you force this motor to do a little more work. Okay? So you might increase the full load current rating of that motor just by a little bit. You may increase that current value to that motor just by a little bit. And let's say that it's about right here. So let's call that 57.75 amps. That's okay. Your overloads, yeah, they're observing that. They're watching that ampacity. They're watching that expanding contractor magnetic field. They're following that current traveling towards the motor in an AC system. That's okay. 57.75, that's not going to hurt your overloads. They're not going to trip at that point in time. They're going to be saying like, hey, listen, we're getting really close. Be careful of this. We're getting real close here. 57.75, you're drawing 57.75. Yeah, okay. All right. That's a little heavy, but don't do it any longer. No big deal. So 57.75, you can draw that to this 46.2 amp full load current rating of the motor, being at 15 horse, but you're kind of stretching it. As the motor is working way too hard, especially for a Class A installation. That means that motor is going to start to create a lot of heat. It's under too much duress. There's too much torque there. And then as soon as that motor, or you force that motor to draw even more, anything slightly above and beyond 57.75 amps, your overloads are going to say, okay, listen, that's too much. We're not going to do that anymore. We're not doing that. Okay, so you might get up to, I don't know, maybe the 62 amp mark up here. That's too much on that motor. Your overloads are going to say, no way, man. You're drawing too much on this motor. I can't do it anymore. I can't let that motor do that work any longer. My conductors are getting really close to their capabilities. No, I'm out. And they open the control circuit. And if you open the control circuit, it's the same as hitting the stop button. It means it's going to shut down everything. That motor stops its operation. You tried to make that motor do too much, and it can't handle it. So the overloads open, which opens your control circuit, effectively stopping the motor from running. And realistically, this motor should not be drawing anything more than 46.2 amps. Nothing more. And you're forcing it to draw 62 at this point in time. So your overloads say, no way, pal. You're done. I'm going to open. And you're going to take some time until I cool down, till I can reset myself. You hit my reset button. Then we'll try again. But we only got the 62 amps, and my conductors are good for 65. So there you go. Your overloads are protecting your conductors. Totally. They saw the 57.75 amps, and they were like, yeah, all right. But then you went above and beyond that, and you pushed that motor to do more, and the overloads were like, nah, that's not going to happen. No, we're not doing that today. No. Just calm it down, bro. It's Wednesday. Really not a big deal. You don't have to get this job done in one day. Calm down. Okay? So 57.75, the overload's open. That opens your control circuit, effectively shutting down the motor. Your overloads are installed before your start-stop stations, or for this week, for everybody, was parallel start-stop stations. And if your overload's open, that effectively opens your control circuit. Your motor will no longer run. You have no control over that motor, so the overload's open, shutting down the motor. Now, your overcurrent protection, this 80 ampere over here, was laughing the whole time. It says, okay, 46.2 amps. Yeah, I'm all right. That's cool. 57.75. Yeah, whatever. 62. Overcurrent over here is like, whatever, man. Do your job. Go back to work. Do work, son. No, it doesn't trip until it sees 80 amps. And even then, it's a time delay fuse. So if that current increases all the way up to something like this, and it sees 80 amps as an RMS, it's still fine. It's still not going to open. It's a time delay fuse. It's not going to open. It says, okay, you're drawing 80 amps for like a little bit. That's fine. That's why I'm a time delay fuse. That's why you put me here. That's why you put me in a 100 amp disconnect. It's okay. I'm going to let that current flow. Or if this was an initial startup and that motor decided that it was going to go from 0 to 1800 RPM within a second or so, it's going to see an inrush in that current. And that's why we size these non-time delay fuses to be 80 amps to provide that inrush current for that motor to get up to rated speed. The fuses are still laughing. They're saying, yeah, man, 80 amps? No problem. I'm still good. But I got a time limit. I'm a time delay fuse. So if you draw that 80 amps for like, I don't know, maybe 5 to 15 seconds, somewhere in there, now I got a problem. So maybe all of a sudden this motor is drawing far too much current and you bump up to 85 amps as an example. Your time delay fuses are going to say, that's okay. I am a time delay fuse, so I'm going to allow that current for a very short period of time. And that might be anywhere between 2 to 15 seconds, 5 to 10, 15 seconds, something like that, to allow that motor to get up to rated speed. But as soon as it sees that 85 amps for far too long, that overcurrent device itself will open if your overloads haven't already. That's the inrush current thing about a motor. It might spike up to 85 amps. Maybe. Every single motor is different. It might spike up to 85 amps. And that's okay for just a couple of seconds for that motor to get up to speed, because realistically you installed number 6 conductors. It'll handle that inrush current as long as it doesn't persist or keep going in that direction. Keep increasing in current, because then your overcurrent protection comes into play. It says, no way, pal. You're at 85 amps for 20 seconds. You're not going to handle that. I'm out. And I open. And that shuts down everything. It's not a reset on a time delay fuse. You have to stop your operation. You have to disconnect everything. You have to go to your main motor control panel, shut down that disconnect so that you can replace these fuses. You have to shut down these conductors up here. You have to turn these ones off so that you can replace these 3 fuses inside that disconnect, because you overload that motor. That motor was never designed to carry more than 46.2 amps, and you forced it to do 85. It's not designed for that. So your overcurrent protection acted accordingly. And that's the inrush thing. It's a time delay fuse. It'll allow the 85 amps for a short period of time, but not for forever. And those fuses will end up blowing if you draw 85 amps for an extended period of time. But here's how overcurrent actually works. It actually works. I'm going to get rid of this here for a second. We know what we're installing. We have an idea of what's actually going on. We understand what's going on with this one specific motor calculation. What ends up happening with that overcurrent device is it's actually observing and watching and waiting for a fault. For an 80 amp overcurrent device for this specific motor, I'll just give it to you right now, coming from table 16. Our bonding conductor should have been a number 8. It would be a number 8 coming from table 16. That number 8 bonding conductor will handle an incredibly large amount of current for a very short period of time, just like all of your conductors will. A 14 gauge conductor will handle 100 amps, but for a very short period of time until it physically melts. Usually what ends up happening with a short is we don't draw 85 amps. We don't draw 100 amps. We don't draw 200 amps. What usually ends up happening with a short is we draw all the amps. As many as could possibly flow, we draw all the ampacity. Kind of like when you short out a car battery and you got your clamps like this, and just to test the car battery, you go pow, like that. There's a big spark. That car battery is probably around the 80 amp range. Maybe a good example, no? So you draw all the current, as many currents will flow, as many amps will flow, as much voltage as you could possibly get. All the current will want to flow because you have a direct short inside that motor. There's a mistake. There's something wrong with that motor. You've got a dead short. That means that you're going right from a current carrying conductor right to your bonding conductor, which is directly connected to your grounding conductor, which means there is no resistance in that circuit. And if there is no resistance in that circuit except for internal wire resistances, like say, the values that we calculated for voltage drop calculations, that's a very, very, very small value. Maybe 1 ohm, maybe, and that's a maximum, maybe 1 ohm. And if it's a 1 ohm resistance in that wire on a 208 volt circuit, that means that 208 amps will want to flow. But then that's a maybe because it's an AC circuit. So now you're talking about impedance, not so much resistance anymore. Now that might be cut down to 1/4 of an ohm, which means you might have like 8 to 1,000 amps flowing. And if it's a dead short and you installed number 8 as a bonding conductor, that provides a very low impedance path back to ground, which means there's going to be an exponential amount of current that flows to this motor on your number 6 conductors and returns on your number 8 bond. So the 85 amp thing doesn't matter anymore. The 62 amp thing doesn't matter anymore. The 57.75 amp thing doesn't matter anymore. Or the 65 amp ampacity of your conductors, that doesn't matter anymore. Or the 46.2 amp maximum full load current rating of your motor doesn't matter anymore, because now you're drawing an exponential amount of current. And once you draw an exponential amount of current, this time delay or the non-time delay or the fact that it might be a circuit breaker doesn't matter. It opens as fast as possible because you are seeing an exponential increase in current flow along this AC sine wave. Exponentially. This could be all the current that would flow. Before your conductors melt, your fuses blow, or your motor explodes. Exponential amounts of current. But what's going to stop that? This overcurrent device. So that's exactly how your overcurrent device protects the fault that's in your motor. Your overloads that were drawn over here protect your conductors because they were rated for 57.75, but your conductors are set coming from table 2 at 65 amps. As soon as you have a short in your AC sine wave, it's going to exponentially increase. And that overcurrent device is going to open as fast as possible, because the reason why you install a number 8 bonding conductor right here is to facilitate the rapid operation of the overcurrent device, coming right back from basic section 0 definition. For a bonding conductor is installed to facilitate the rapid operation of an overcurrent device. And if all of a sudden that overcurrent device sees more than its maximum of 80 amps coming up here to an exponential, this is the infinity symbol right here, an infinite amount of current coming through, that overcurrent device is going to be facilitated rapidly via this number 8 bonding conductor. When we have a fault, we want all of the current to flow so that it opens my overcurrent device as fast as possible. This is why you install fuses and circuit breakers. Not to limit current. It's not to be like, oh, you're drawing 16 amps. That's too much. I'm going to shut off 15 amp breaker. No, it's because you're drawing 4,000 amps on a short. Kind of cool, right? So, prime example on how your overcurrent devices are actually operating in a circuit based on a continuous duty Class A motor. The difference between your overload protection and your overcurrent protection based on the conductors that you install for this 46.2 amp full load current rating of the motor. That's fun, right? There's a little bit of instrumentation, there's a little bit of electronics, there's a little bit of theory, there's a whole bunch of code for you to study for that specific motor. Now, I am going to leave you with that. I'm going to leave you with that concept. And then when we come back on Friday, I'm going to reinforce this knowledge. And we're going to go a little deeper into motors. We're going to start looking at different types of motors, different overcurrent protection. We're going to look at thermomagnetic motors, different types of conductors. And then everybody's loved calculation, a voltage drop calculation when it comes down to motors. Okay, so I hope you guys appreciate this lesson today. I once again apologize for that very first calculation with the time delay thing. I apologize for that. That won't ever happen again. My sincerest of apologies. I hope you find value in this video. Watch it as many times as you want. Go back through, do this calculation again, and I will have more sheets ready to go for you on Monday, Tuesday, or Thursday when I see you again in person. I will see you again on Friday, so I hope you have a wonderful afternoon. I'll talk to you guys in a little bit.